In our last lesson, we learned how to draw Lewis structures. And of course, that's only the first step to figuring out if a molecule is polar. So in this lesson, what we're going to be looking at are the next few steps, which are how to use that Lewis structure to find the shape of the molecule. And the way we're going to do that is first we're going to determine the number of electron groups in that molecule that are around the central atom. We're going to draw a 3D model based on one of 5 shapes. There are only 5 shapes that covalent compounds can take. And then we're going to draw in those bond dipoles, if there are polar bonds, and see if those bond dipoles cancel. We're going to use the original compounds we had in our Lewis structure drawing to help us out here, because they also exemplify a variety of shapes and a variety of problems that come up as you try to decide if the molecule is polar. Now, I do want to bring this up right now, which is it possible to tell if a molecule is polar without drawing the Lewis structure? And the answer is no, not if you don't have some inside information. And the reason is because what we're really trying to find out to determine the shape, what we really need to know is we need to know, are there lone pairs on the central atom? And you can see that without actually drawing it, it would be very, very difficult to know that answer. So you need to draw the Lewis structures first. The other thing that you should know about Lewis structures is Lewis structures themselves, they do not show shape. So how we draw the true shape of the compound, and we need to know the compound. So let's take an example. If we look at the very first one, you'll see that I drew it sort of where the oxygens were spread out in kind of like a T shape. But that's not really the shape of this compound. This compound is Trigonal Planar. And it's not just the name that matters so much, it's how it actually looks. It looks more like a Y, right? Not so much a T. As a matter of fact, when I look at all of these, I've been doing Lewis structures for a long time, I've been doing VSEPR theory for a long time, I know what these shapes are going to turn out to be, and pretty much none of them actually look how they look when they're originally drawn in their Lewis structure. Like this one looks like a cross, doesn't look anything like a cross when we actually figure out its shape. Probably number 4 is the one that's going to turn out to be most like how it's drawn. We'll see though. So how do I get from the Lewis structure? If it does not show the shape, how do I get from the Lewis structure to the actual shape? Well, there's sort of a process you need to go through. Determine the number of electron groups around the central atom, which will tell you sort of its shape. Because what we're doing here is we're using a theory called VSEPR theory, VSEPR, which stands for Valence Shell Electron Pair Repulsion theory. In other words, the idea is that electrons repel each other, so they'll push back. So if you have 2 bonds, they're not going to want to be close to each other. They're going to spread as far as they possibly can. And a lot of times just simply knowing that, it'll give you a feeling for the shape. But we're going to figure out how many electron groups there are. We're going to decide which one of the 5 main shapes it's going to take on. And then we're going to draw a better 3D model of this particular Lewis structure. In order to do that, let's start with figuring out how many electron groups each one of these compounds has. So if I look at the first one has 3 electron groups originating from the central atom. So the sulfur has 1 direction going for the double bond, 1 for the single bond, and 1 for that single bond. That's 3 electron groups, 3 directions from that central atom. The double bond is just 1 electron group because the 2 bonds go in the same direction, right? We're talking about more or less how many directions go from that. If we were to look at the selenium here, the selenium has 5. It has 4 bond directions and 1 lone pair direction. That's 5 total. So it has 5 electron groups, or 5 electron domains, sometimes it's called. The next one, easy, right? There's only 4. 4 bonds, 4 directions, we're done. What about number 4? Well, there are 5 directions in that one as well. There's 1 bond, 2 bonds, and then 1, 2, 3 lone pairs. So 3 lone pair directions, or electron domains, and 2 bonding ones. What do you think for number 5? Well, I see 4. There's 1, 2, 3 bonds, and 1 lone pair direction. And then, of course, in the last one, there's just 3 electron domains. Now, why do the electron domains matter? Because what that means is the ones with 3 electron domains, like number 1 and number 6, they should have a very similar shape. And you kind of see it. I drew them both as T-shaped. That's not what they are, but you can kind of see why that might be. But it also means that number 3 and number 5 should have very similar shapes. You might be able to see it, but maybe not. In any case, we're going to see in just a second. And number 2 and number 4 here should also have very similar shapes. There's only 5 types of shapes, and it has to do with how many electron domains there are. All right, now we're about to remind you of what those shapes are. So if you're not super familiar, like I don't really know what a trigonal bipyramidal molecule looks like, and I don't know its bond angles, you're going to need to know those shapes, and you're going to need to know those bond angles. So you might want to get out some notes, because we're really quickly going to review them and show you a way that you can access them without having to have a chart or memorize them. All right, now AP does not give a reference sheet. I'm emphasizing this because in CP Chem we did. In other words, you have to know all these compounds, you have to know their names, and you have to know their bond angles. And sometimes that can seem like a pretty tall order, but if you spend the time to understand where the names come from, it makes it a lot easier. And remember, there's only 5 main shapes. Now you know there are subshapes, and we're going to get to that in just a second. But let's look at these. AP does not give any reference sheets, so we've got to make sure that we have them. There are only 5 main shapes, and these are called electronic geometries. Now, AP will ask us in questions, what is the geometry of this molecule? And that's what they mean. What is the shape? Same thing. Okay, so if we look up here, we see that more or less what's going on is we have one central atom in each case, the red one, and this is what the shape will look like if we have 2 electron domains, 2 directions, right? This is what it'll look like if we have 3 electron domains, 4 electron domains, 5 electron domains, and 6 electron domains, which is the most you can have because after a while you just run out of room, right? Where do the names come from? I think linear is the most obvious, just means straight. Trigonal planar, of course, well, let me show you. Trigonal planar is called trigonal planar because when you rotate it on the side, you can see it's flat, right? Trigonal means 3, planar means flat. Hey, while we're here and we're using this simulation, VSEPR theory is talking about the repulsion of electrons. I like this. You grab this and try to pull it near it. See how they all try to repel away? Pretty cool, right? By the way, this is a PhET site. If you've never been there, you're welcome to go check it out. Yeah, so that one's trigonal planar. Now, let's go back and do a little bit of labeling of bond angles there. You know that if we were to have 360 degrees in a circle, if we divide it into thirds, then clearly that bond angle is going to be 120. Whereas up here, the bond angle from there to there is just 180 degrees. Now, if we get to 4 electron groups, now this is the one that, I think it makes sense. If trigonal means 3, tetra does mean 4, right? Like the game Tetris is full of blocks, 4-sided blocks. That's why it's tetra. The bond angle here is probably the most difficult one to remember. It's 109.5 degrees. And then if we get down here where we have 5 electron groups, well, let me show you this one. This one's referred to as trigonal bipyramidal. Well, if we were to go look at our simulation, in our simulation, you can see that it's called trigonal because if I rotate it this way, you can see these 3 atoms make a trigonal planar structure. And then you just have an atom on the top and an atom on the bottom. So you can imagine that the bond angles are going to be, well, from there to there are going to be 120, and from, let's say, the top to any of the sides are going to be 90. So they're going to be 2 bond angles on this one. So there we have 90 degrees and 120 degrees. 120 degrees along the belt line, 90 degrees. Now, this is probably the trickiest one to deal with, and we're going to talk about as we look at subshapes. This is the one I think we're going to want to pay the most attention to because it's the most challenging. And then octahedral down here, you can see all of the bond angles are just 90 degrees. Let's talk names a little bit. Why is this trigonal? Well, we talked about that. Why is it bipyramidal? It's because if I were to draw a, let's get a marker. If I were to draw lines that connected these, you would see there's sort of a point on top that makes a flat-sided pyramid on the bottom. And that is the first pyramid. The second pyramid is pointing down. So that's why it's bipyramidal. Okay, so we've figured that out. And then why is the last one octahedral? Well, it turns out that even though there are only 6, and you might say, why not hexahedral? Up here when they were talking about tetrahedral, they were never ever talking about how many atoms there were. They were talking about if you drew those lines, you see there's one triangular face here, there's another triangular face there, there's one on the backside over here, and there's one on bottom. There were 4 faces. Well, here, if you were to do the same thing, if you were to draw those faces in there, there's one there, there's one going down the backside like that, one on the backside over here, and one over there. That's 4 faces, and then of course there are the same 4 faces on bottom. So it's referred to as octahedral because it's talking about how many faces there are, not how many atoms there are. I'd say that's the one name-wise that's the most tricky to figure out. Okay, so let me pick a nice marker color here. Now, how do we figure out what the subshapes are? Well, the subshapes are pretty easy to work on. You can imagine, linear doesn't really have a subshape other than, you could say, well, if I only have 2 atoms, obviously that's going to be linear, right? And there really is no bond angle. But let's look at this. The first subshape has to do with if I replace one of these atoms with a lone pair, and the other 2 I keep exactly the same as I had before. So going that way, and I replace this one with a lone pair. And you can see as soon as I do that, the bond angle hasn't changed. It's still 120 degrees. There's not much difference, except for now the shape, if I were to cover up this lone pair with my hand, I mean, it's still there because if it wasn't there, the 2 would spread out like that, right? But if I were to cover it with my hand, you would see what's left of the molecule part of it is referred to as bent, right? Because it's bent. The British call it angular, right? Seems reasonable either way. Let's try this one. If I swap out one with a lone pair, let's see, I'll do the one on top, and I were to go like that, and like this, you would see that that trigonal is not flat, right? Let me show you. So if I get rid of one of my bonds and I throw in a lone pair, you can see that the trigonal, all I've done is replace, it's kind of like a tripod, right, with something coming from the top. It's definitely not flat. So it's trigonal, but it's not planar anymore. It's trigonal pyramidal, right, or pyramidal. But if you want to sound sophisticated, organic chemists would say pyramidal. Now, not a lot's changed here, though. Of course, the bond angles are still 109.5. We said our name was going to be Trigonal Pyramidal because it's pyramid-like. All right? As long as we're here, we're going to talk about one thing that's super important here. When I said the bond angles are 109.5, that is not 100% true. You may or may not have learned this in CP, but you need to know this in AP. So the bond angles for this one are actually slightly less than 109.5. Why? Because this lone pair is more diffuse. It takes up more room, and since it's going to spread out more, it's going to squish those bonds down below. So same goes here. This lone pair is more diffuse than a bond, and so therefore it's going to squish that bent angle down a little bit, and so it's going to be a little bit less than 120 degrees as well. And the more lone pairs you have, the more squished that angle is going to be. Now, it's not going to be a lot less than 120, maybe 119 point something, but it'll be slightly less. Now, let's look at this one. This is the trickiest one of all, and you have to decide where the lone pair goes. Now, the way I see this is I see this kind of like, well, I don't just orient this any old way. I always orient it so that that trigonal planar part is along what I call the belt line, right? It's along the belt line. And so it's got this kind of belt going around it. And on top, this is the head, and these are the feet. And the rule is, don't ever put a lone pair on the head or the feet. Always lone pair along the belt line. Always, always, always. So this is the hardest one of all. And let me show you what I mean by that. If I get rid of one of these and I add in a lone pair, you can see that it went along that trigonal planar belt line. If I were going to do it again, it would go along the belt line. If I were to do it again, it would go along the belt line. So the rule is, always lone pairs along the belt line. Don't touch the hair. Don't tickle the toes. You know what I mean? Can't touch the head and the feet. So let's go back and look at our our little map here. So if we have one lone pair, we know it. Don't touch the hair, right? That's the, don't touch the hair. Don't tickle the toes, right? Don't tickle the toes. Those are toes. Always put the lone pair along the belt line. And the rest is all the same. What are the bond angles? Well, from here to here, we still have 120 degrees. Nothing has changed. Although probably slightly smaller than that at this point, right? Smaller than 120 because that lone pair is going to squish down those bonds. And then from the top to the side, we still have 90 degrees. And we've got to come up with a shape. Well, the shape you may have seen, if we go back to our simulation, this is probably the weirdest one of all. If I were to show it to you, let's see, let's get the molecular geometry on here. You see they say it's seesaw. Why seesaw? What they mean is like, you know, a seesaw at a playground. If I orient it, let's see if I can, let me grab this one, pull it down here like that. You can see that right here, it looks like a seesaw. These are on the ground, the kid sits there, the kid sits there, and then you kind of go, you know, and you're sitting up here and you're saying, don't jump off. You know what I'm saying, a seesaw? So it's a seesaw. All right, and then let's get to our last one here. This one doesn't matter where the lone pair goes. I'm going to put the lone pair on the bottom. You'll see why in just a second, but it does not matter quite so much. So what this one is this is kind of like, there's my lone pair. Meant to be a lone pair there, not a bond. In any case, so when you get to this one, you can put the lone pair anywhere, and you can see that it's a pyramid. Right? It's a pyramid where the base has 4 parts on it instead of 3, right? So therefore, we're going to refer to it as square because square means 4. You might say, why not tetra? And I hear you if you're thinking that. Square pyramidal, or pyramidal if you wanted to sound a little bit more like an organic chemist, right? Square pyramidal. What are the bond angles? Still 90 degrees all the way around. You could say from there to there and bottom. You could say 180 if you want to. But remember, it's going to be slightly less than 90 because all of these are going to be sort of squished up away from that lone pair. And there we go. Now, so those are my kind of silly drawings. Here they are a little bit better with their names, but not with the bond angles. Those are slightly better drawings. Now you could do the same thing again. So if that's one lone pair where one lone pair went there, let's try a second lone pair. Well, this one doesn't actually have a second lone pair, so it's out. This one does. If I were to add, let's say I'm going to add it, I don't know, the back there. Let's go like that. And I were to go, leave that one, lone pair, like that, you can see what I'm left with now is bent. And my bond angle still 109.5. But now even smaller, right? Even smaller because you have 2 lone pairs that's going to squish it down even more. If I were to look at this one, you remember this is the tricky one. Where does the lone pair go? On the belt line, right? Remember, we've got the belt line here. Don't touch the hair. Don't tickle the toes. It's got to go on the belt line. So boop, boop, zoop. Don't touch the hair. Don't tickle the toes. So I'm going to put this one in the back. And then you can see now it looks like it's T-shaped, right? T-shaped. Seems reasonable. Bond angles? Well, now you notice we've gotten rid of that 120 because we don't have 2 belt line ones anymore. We only have 90 degrees, right? And there's something really kind of unusual going on here with this one. So let me get rid of a bond, add a lone pair. Come on in here. So you can see definitely T-shaped and definitely went around the baseline. But if I were to say to you, would the bond angles here be smaller because they were squished by the lone pair? The answer is no, because you have symmetrical lone pairs here that will be pushing on this bond. There's nothing squishing these down like this. So you're not going to see much of a decrease in angle here. So it really is going to be about 90 degrees. So unlike the other ones, it's not going to be less than 90. It really is going to be 90 degrees. All right, and then let's look at the octahedral. Now, octahedral, because lone pairs spread out more, right, the next lone pair is going to want to be on the opposite side. And the reason is because since they spread out more, they're going to repel each other more. They're going to want to get as far away as they possibly can. So if I put the first one on this side, the second one's going to have to go on its opposite side. Then you're still going to have this one going forward and back, and that one like that. And my drawing is pretty darn awful. Let's see if we can go back to the simulation and see what the simulation would look like. All right, so let me get a couple, oops, let's get rid of boop, boop. All right, so that should be octahedral with 2 lone pairs. They always end up opposite each other because they're just bigger and they're going to repel each other, so they're going to want to be as far away as they possibly can. Bond angles, still 90 degrees. And here, they're not going to be squished smaller either because they're symmetrical around the lone pair. So they're going to stay exactly like that. Now you can see what it's going to look like. First of all, is it going to be trigonal or square? And is it going to be pyramidal, pyramid-like, or planar? Definitely it's going to be square planar. I don't know what I was thinking there. Square planar. So let's go back and label that. All right, so I have it labeled down here, square planar, 90 degrees, not going to be squished at all. It's going to be exactly 90 degrees because the lone pair is symmetrical. All right, so the better drawings are right here. You can see my bent, T-shaped, square planar, looks pretty good. And then we've got to get to one more lone pair. Now this one, of course, doesn't have another lone pair, but this one potentially can, right? You could end up with, let's see, if we already have it here. Remember, this is the one. Don't mess with the hair. Don't tickle the toes. It's got to be along the belt line. So you're still going to have your hair. You're still going to have your toes, and then now you've got lone pairs all along the belt line. And what shape is it going to be? Linear, because it's going to be straight, just like that one up there, right? And it really is going to be a bond angle of 180 because, again, you have symmetry of those lone pairs, so they're not going to squish down the bonds in any way. If you were to look down here and go for another lone pair, now it could go anywhere, so I guess I'll put it on bottom. So if I go, whoop, lone pair, lone pair, lone pair, then I have up, out, and out, like that, you can see pretty darn quickly we're going to end up with T-shaped. Bond angles are still going to be 90 degrees. However, here, let's look at the model and see if we think it's going to be greater than or less than, or... So T-shaped for sure. I think the bond angles, like these two, are not going to move those bonds either way, but you can see this one down here is going to press this one up. It's going to press this one up. I think you're going to get slightly less than 90 degree bond angles there. Just a little bit less. All right, and there we go. I've got it labeled less than 90 degree bond angles, and my drawing's a little bit bad, but there you go. So you should get these two pushed backwards just a little bit, okay? Now you can see that my note which popped up a little bit earlier here is understand AP does not say the term shape. They say geometry, but that's what they mean. When they say, what is the geometry of this molecule, they want to know what is its shape. But when they say it, they are not going to ask you, is it the electronic geometry, as in which main shape is it? And you have to wonder, do they want the main shape or do they want the subshape, which is referred to as the molecular geometry? They always want the most specific geometry. In other words, they always want the molecular geometry. If it's T-shaped because it was a trigonal bipyramidal that had 2 lone pairs, you want to refer to it as T-shaped, not trigonal bipyramidal. If it doesn't have any lone pairs and it really is trigonal bipyramidal, then by all means call it trigonal bipyramidal. But they want the most specific shape, the molecular geometry at all times. I've never seen them ask for the electronic geometry in any way. All right, so if we go back and look at our molecules, let's see if we can determine if they're polar or not. First step, since we've already decided this one has 3 electron groups, we got to figure out what shape it is. Well, 3 electron groups is quite clearly 1, 2, 3. It's quite clearly trigonal planar. So I'm going to draw this thing in the shape of a trigonal planar molecule. So there's my main shape. I know the thing is going to be trigonal planar. There are no lone pairs, so it really is going to be trigonal planar. We know that its bond angles are going to be 120 degrees. They're not going to be less than that. They're going to be exactly 120 degrees. And if I were going to draw it more accurately, I'd have to have an O there, an O there, and an O there. Let's see if I go S. And since I'm just trying to figure out shape, I'm probably not going to draw in all the lone pairs. I mean, I drew a good Lewis structure over there. And we get to this point, so this is a more accurate shape. If I were to then draw in the dipoles, well, oxygen is more electronegative than sulfur. If I draw in the dipoles like that, you can see that those dipoles are perfectly symmetrical, right? You can imagine that if you were here and somebody was pulling on ropes in these directions, they're perfectly offset. And so therefore, this is going to be a non-polar molecule because those bond dipoles offset. All right, let's go to the next one. 5 electron groups because there were 4 bonds and 1 lone pair. That looks like trigonal bipyramidal. And this is the one we've got to be careful of. Remember, don't mess with the hair, don't tickle the toes. So we know it's going to take on this shape where I can't touch the hair, can't touch the toes, but it's going to look roughly like that. There's 1 lone pair. Do you remember where the lone pair goes? On the belt line. I'm going to put it right there. So my molecule is going to have an SE here. It's going to have the lone pair there. I'm trying to draw it exactly like that. It's going to have a bromine going off in this direction, a bromine going off in this direction, and a bromine going off in this direction. There's the head. There's the feet. You know that the bond angles are going to be 120 here, but slightly less than 120 degrees, and 90 from the top to the side, but slightly less than 90 degrees. And we know that its shape is going to be, yes, it is going to be trigonal bipyramidal, but once we get down to the molecular geometry, which is what AP cares about, what shape do you think? It's going to be seesaw, right? Seesaw. All right, and is it going to be polar or not? Well, bromine is more electronegative than selenium. Actually, I'm not 100% sure of that. We could go back and look. But they're different atoms, so therefore there has to be a difference in electronegativity. So I'm going to suggest that that's true. You know that if I was wrong, the arrows would be going the other way. And I see that the top and the bottom, the bond dipoles will offset. But there's nothing going this way where there's nothing on the other side to offset those bond dipoles. And that's an important thing to know is the reason you don't want to talk about the lone pair having a major role in this is because a lone pair is like a rope with nobody pulling on the other end. So there's nothing, no electronegative atoms pulling the electrons this way. So these two, which are headed off in one direction, actually let me get it more like headed off in one direction, there's nothing on the other side to balance them. So yes, I definitely think it'll be polar because those bond dipoles will not offset. Boom. This molecule, if it were to be around another one, would have dipole-dipole intermolecular forces between it and another molecule. I am really clicking a lot of buttons here. All right, let's get rid of me and let's keep going. So if we were to do this next one, it has 4 electron groups because there's 4 bonds. Clearly that's tetrahedral. If I draw a general tetrahedron to guide my 3D model drawing, boom, 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 things look great. It looks like a tripod with something coming from the top. The bond angles for sure, because there's no lone pair, will be 109.5. It will be tetrahedral. And it's going to look just like that with my N in the middle and H on top and H this way. Make my little tripod. Looks pretty good. By the way, I actually think H is slightly less electronegative than nitrogen, but you could look it up. So I think the bond dipoles are going to be going inward. And you can see that tetrahedron is a perfectly symmetrical shape. It is very symmetrical. Symmetrical. And because it's symmetrical, that means that all of those bond dipoles are going to perfectly offset, and you're going to get a non-polar molecule. Now, let me stop right here. Actually, nope, I'm going to come back. Let me put a little star here, because you guys are going to freak out about what I'm about to tell you here. Let me put star. This is me to come back at the end to this one and this one. All right, let's keep going, and we're going to come back to those two at the end. We're going to do a little more talking about them. This one, 5 electron groups. I think it's going to look like a trigonal bipyramidal. Remember, don't touch the hair, don't touch the feet, don't tickle the toes. We're going to put all of those 3 lone pairs along the belt line. Bromine, there's the hair, there's the feet, lone pair on the belt line, lone pair on the belt line, lone pair on the belt line, and you can see definitely it's going to look like linear. Its bond angles are going to be 180, and really 180, not less than that. Is it symmetrical or asymmetrical? I think it's symmetrical. Because, I'm going to stop right there, if bromine is more electronegative than xenon, you can see those bond dipoles will offset, and it will be nonpolar. So therefore, a xenon bromide molecule, dibromide molecule, will not have dipole-dipole interactions with another xenon dibromide molecule. All right, pretty good. Let's keep going. If we get down to this one, I have, let's see, 1, 2, 3, 4 electron groups. Looks to me like it's going to be tetrahedral. 1, 2, 3, 4. Looks great. So I know it's going to be this generic shape. We know the bond angles are going to be about 109.5. I'm going to put the lone pair on top, but you can do what you think is right. I'm running out of room here, but we're going to go phosphorus. Oop, I'm not doing a good job. Let me erase. Lone pair on top. I don't like that lone pair. Let me see if I can draw on the dots a little bit better. That's meant to be a lone pair. Oxygen, oxygen, oxygen. All right. Bond angle is going to be slightly less than 109.5. It's going to be what shape? Trigonal for sure. Trigonal planar or trigonal pyramid-like? What does it look more like if I cover up this one? I think it looks more like a pyramid, so I'm going with pyramid. All right. And then, will it be symmetrical or asymmetrical? Definitely asymmetrical. Why? Because when I draw on the bond dipoles, oxygen's more electronegative than phosphorus, I believe. The bond dipoles, you can see, will all be pulling slightly downward, and there's nothing on the other side to offset them because there's no electronegative atom on the lone pair side. So therefore, the bond dipoles will not offset, and you'll end up with a polar molecule. So PO3 definitely could do that sort of interaction with another PO3 molecule. And then let's get down to BCl3. Let's see, it has 3 electron groups, so therefore it's going to be trigonal planar. It really is going to be trigonal planar or pyramid. That one, if I rotate it around, will definitely be planar. And is it symmetrical or asymmetrical? Do the bond dipoles offset? Yes, the bond dipoles offset because they're all pulling in an opposite direction. It is a symmetrical molecule. It's a funny M I just drew. And therefore, if it's symmetrical, the bond dipoles will offset and it will be nonpolar. All right, now we've got to get back to those blue stars that I was just putting up there. Why did I put those blue stars up there? Well, let's look back at our polar molecules. What polar molecules mean, remember we started with H and like F, and we said that there would be a net flow of direction. There's a partially negative and a partially positive side of this molecule. So therefore, if I were to say a molecule was polar, like this one and that one, I would have to say which side of the molecule is that negatively charged side or positively charged side. Well, this one, if you look up here, you can see that, these 2 bond dipoles will offset. I think the electrons are flowing mostly over to here. This side of the molecule would be negative, and the opposite side over here would be, I don't really know what just happened. This side of the molecule would be partially positive, just like up here with H and F. So therefore, you can see that this side of the molecule would be attracted to the positive side of a molecule in a dipole-dipole interaction. Polar molecules have a partially negative and partially positive side. Now let's go back and look at this one. Do you see how based on shape I decided it was nonpolar? Well, there's one other thing to consider. We did not, for this compound, need to go through this entire thing because it doesn't have a partially positive and negative side like that. It has a flat-out, full-blown positive charge. If it flat-out has a full-blown positive charge, that's better than a partial. It is polar. Matter of fact, it's not just polar, it's the most polar kind of compound. It's an ionic compound. So therefore, this one I didn't need to run through it either. It is polar. Why is it polar? Because it's more polar than a polar covalent compound. It's flat-out ionic. So anything that has a charge is going to be polar, regardless of its shape. And as a matter of fact, it's customary to come in and when you draw the Lewis structure, put brackets around it and put a little positive charge up there. All charged species, you should put a bracket around the Lewis structure and put its charge on the outside. That's the customary approach. And the reason is because this is the phosphide ion. This bracket with a negative charge is saying, look, this thing needs a positive ion near it. It's ionic. So for charged species that are ionic, you don't need to go through this process. You know they're polar because ionic is as polar as you can possibly get. But for non-charged covalent compounds, you need to draw the Lewis structure. You need to determine the electron groups. Draw a good 3D model. Decide if the molecule is symmetrical or asymmetrical, and then see if those bond dipoles offset. All right. Now, other than deciding if something's polar or not so that we can decide if it can have dipole-dipole intermolecular forces. I know this has been a very long way of figuring out if a molecule can have dipole-dipole intermolecular forces. But the other thing AP is going to do is they might just ask you to explain why a molecule is polar. And I don't think these things will surprise you, but I'm telling you this because this is something that people get wrong a lot. When I'm at the AP reading, more students get these problems wrong than get them right. So let's see what you should do. Draw an accurate Lewis diagram. State the geometry of the molecule. I think it's trigonal pyramidal, right? State if the molecule is symmetrical or asymmetrical. You need to use those two terms. And of course, symmetrical means you think the bond dipoles offset. Asymmetrical means you think they don't. And then state whether the bond dipoles offset. Because it is asymmetrical, the bond dipoles do not offset. And then, therefore, the molecule is polar. Very simple. It really is kind of a 3-line process. So how can it go wrong? Why do students miss it? Well, it's because a lot of times in first-year chemistry, and we see this all around the country at the reading, students are taught a molecule is polar if it has a lone pair. It's a shortcut for determining it. Hey, that molecule has a lone pair. Therefore, the molecule is polar. Well, for starters, that is not true. There are nonpolar molecules that have lone pairs on the central atom. And secondly, it's not a rationale that rests on any understanding of bond dipoles. And they really want you to draw on bond dipoles and explain what's going on with the flow of electrons in a molecule. So things to avoid doing, and this is going to be hard, many students say that the molecule is polar because it has a lone pair in the central atom. If you go down that route, you're going to lose credit. It is not true that if you see some molecule with a lone pair that you can stop right there because it's polar. You need to make the argument about the bond dipoles and the shape of the molecule.